It's kind of washed out, but we see this is the WISP, again, no batteries, and we're powering up, turning on the microcontrollers, interpreting the protocol. We're going through measuring the acceleration down, so we always have 1 G of acceleration down. And now as I rotate it around, I'm wirelessly sending that data back. So, really, this is like a Wiimote without any batteries, basically, the same type of thing. So, this is something you can just go download. If you get the WISP, you can download this application, get running up in probably like 10 minutes or so. There's some other cool things to kind of get an idea of what the... Sure.
This is probably a really dumb basic question, but what is it that you have that's doing the reading right now? What hardware is doing the reading?
So we have an RFID reader hidden underneath the table. It's sending out, it's sending out data.
So how good does this RFID reader have to be? Is that part of the WISP package, or could I buy the $50 thing that's advertised on the back of Nuts and Bolts magazine to plug into the USB?
So this is Impinj. So we're using standard off-the-shelf RFID readers. So this is. Right. Oh, so sorry, I thought you were adding in, but let me just finish that one real quick, and then I'll get to that question. I think the readers are about 1,800. I don't know. It depends if you have the academic discount or whatnot. And then they have multiple antennas. So, and then what's doing here is the actual MSP430 is doing the protocol on this side, interpreting, is it my turn to respond? Oh, yes, it is, and then transmitting data back.
What happens if a second RFID tag is in the field, because then the anti-collision might be different?
So we're not using all the ID space. We're just we have a little header that we've. Okay, yes, they know. I'm a hardware guy. I don't know. Yeah.
Yeah, one more.
Sure.
Does it implement EPC Gen 2, so anti-collision? I didn't get that last one.
He's going to talk about
collisions.
Yeah.
Oh,
he's got it.
Does it do pseudo-random number generators? Yes?
Yeah.
Okay.
Yeah. I mean, we didn't implement every last little detail of the Gen 2 spec, but it is compliant. It works with other things. Okay. What's this guy? Oh, wait. And this is just a fun demo. So you guys probably can't see it, but there's a little LED blinking. So it's blinking now. You see even blinking now. So, it's nice. You can kind of get a sense of what the range is. So yes, you probably can't get really fast update rates, but you can get some update rates, right? So you can kind of get a sense, you guys can play with this later, about what the area of which you can actually cover with the RFID reader is. All right. So quickly back to tutorial.
There's a really great video online of some artists, I think somewhere in Europe, that used an LED to paint the antenna. I don't know what you would call it.
Yeah.
Radiation pattern.
So basically what they did is they took time-lapse photography and moved this all in space, and you can imagine that you'd see all these little points in light in space that would show where this thing could turn on. It was pretty cool. At first I was like, wait, that's not a radiation pattern. And I was like all mad because they're not antenna designers, but they did a great job. So now we've kind of talked about the space of this real-time WISP, right, where I send power to it, turns on, it spends data out, and it's kind of done. There's this other mode that Dan kind of explored where you put a super cap on it. So now you go and store charge maybe overnight, and then you go out in the world and do some sensing, kind of maybe more in the moat space. This was, I put this slide in here. This was a paper where we actually had a touch sensor, so we could actually send data into the tag itself by touching the antenna or not touching the antenna. We weren't detuning the antenna. We were actually telling the tag, this is one state, and then this is another state. What was really cool about this is we prototyped this in probably about half a day, like one afternoon, and it took us the next month to write up the results. But basically all we had to do is have this RC filter that, we were changing the capacitance, and you could just, wire that right into the ADC pins. And if you're responsible about it, now you can go and have this new device that didn't exist before. You certainly couldn't do that in silicon in that time frame. And again, WISP Challenge is up and running. We're going to reopen it, and you guys are invited to submit applications. Great.
Okay.
Okay, go ahead. Michael
ready?
Buettner, you'll
All right.
give the second tutorial presentation.
So the purpose of this is to talk about and explain what the Gen 2 protocol is, how it works, kind of go over the details of the Gen 2 standard as specified by EPC. And then what I'm going to talk about is, okay, well, what part of that does the WISP implement, and how does it interact with the readers? So hopefully it'll answer some of the questions that came out of the last session. And a lot of this will probably be review for people here. So just to get everybody on the same page, there's many different types of RFID. One type is the active RFID, which you'll see in kind of your speed pass. There's a power source in the tag, so it can get transmit ranges of 30 meters. This is not the RFID we're interested in. Second type is high-frequency RFID, so you have a range of about 10 centimeters. This is what you see in your credit cards, your passports. This is not the RFID we're interested in. This is the one we're interested in, so passive UHF RFID. So this is in the 900 megahertz range. It's the same type of RFID that's used for Walmart supply chain monitoring. And this is the same frequencies and technologies that the WISP use. So UHF RFID was initially kind of initially designed to replace barcodes. So the idea is instead of having to have a optical scanner and holding it right up, you can now read object identities from 10 meters away, no line of sight, and very rapidly. So there was a number of different standards and different technologies. In about 2005, EPC Global standardized it as what's now the Gen 2 protocol, which is what the WISP uses. And what this did is really kind of helped the industry at large focus on one technology, which ended up coming out with lots of readers, lots of tags, reader prices coming down, which is great. And it's also been used for applications beyond just supply chain tracking. So now instead of tracking pallets, which is how it used to be used, there's actually some places tracking, over 150,000 individual items on the retail floor, which is a pretty big step as far as RFID goes. And there's also applications. So one thing that's happening at the University of Washington is we have RFID readers in all of the hallways. So they're actually looking at, so what are the privacy and kind of social issues that come up when people are being tracked, their objects are being tracked over a large space. So I don't know how many readers there are, but many, many readers. And also now the U.S. passport card and enhanced driver's license have Gen 2 tags in them. So a lot of people, me for instance, are actually carrying around a Gen 2 tag in my wallet. So the nice thing about all of these different applications is that it's really driving this whole industry, and the WISP is riding on the back of that. So now we can get these readers that are pretty high technology. They're relatively cheap because they're not made for the WISP. They're actually made for Walmart. So now into some of the nitty-gritty, which is the Gen 2 PHY layer. So as I was saying, and this is specific to the U.S., so anybody in Europe, I'm not actually sure about all the details of how it works there. But in the U.S., it's in the 900 megahertz ISM band, and the FCC says if you're going to operate in that band, you have to change channels every about 400 milliseconds across 50 different channels. So as these tags are passive, the way that it works, the RFID reader transmits 1 watt worth of energy. The tag harvests this energy, powers up, and the way that data is transmitted to the tag is the reader has to keep on that carrier wave to continue giving power to the tag. And then what it does is just have very short periods of low amplitude. And the tag can very simply see what the period is between these pulses of low amplitude, and then it can figure out whether it's a 0 or 1 being transmitted from the reader. And you can get, a variety of different downlink rates using this. And that setting is set on the reader. So in the uplink, since these tags, again, don't have a power source, what they do is change the antenna, the reflection coefficient of their antenna. So basically what they're doing is reflecting the transmitted signal, which is coming from the reader, and the reader can then detect the variation in that reflected signal to decode the bits. And there's 2 parameters that define the uplink from the tag to the reader, and the reader tells the tag which settings to use. So the first is the link frequency, which is from 40 to 640 kilohertz. And the WISP, for instance, uses a 256 kilohertz uplink. But there's a second parameter, which is the uplink encoding. So the simplest encoding is called FM0. So if you want to, show a 0, then you just have a transition between either reflecting or not reflecting, 1 transition per bit.